Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Firdaus bin Madrusham. Today I want to explain about Jacobi method hand calculation. So, as you can see, we have three equations with three unknown, which is the first equation is 5x minus 2y plus 3z equals to negative 1. The second equation is negative 3x plus 9y plus z equals to 2. And the last equation is 2x minus y minus 7z equals to 3. So what we need to do is, for the first equation, we need to let x be on the left side. So the first equation is 5x minus 2y plus 3z equals to negative 1. When we let the x be on the left side, it will be x equals to negative 1 plus 2y minus 3z over 5. Okay, let's continue to the second equation. This time, we need to let y be on the left side. So for the second equation is negative 3x plus 9y plus z equals to 2. And when we let y be on the left side, it will be y equals to 2 plus 3x minus z over 9. And for equation 3, let z be on the left side. For the third equation is 2x minus y minus 7z equals to 3. And when we let z be on the left side, it will be z equals to 3 minus 2x plus y over negative 7. After we rearrange the unknown as the subject, then we need to follow the setup iterative formula. So for the first equation, x k plus 1 equals to negative 1 plus 2yk minus 3zk over 5. For the second equation is y k plus 1 equals to 2 plus 3xk minus zk over 9. And for the last equation is z k plus 1 equals to 3 minus 2xk plus yk over negative 7. So the letter k plus 1 is actually the number of iterative. For example, if the k is 1 and the iterative is 2. To solve the problem, we need to take initial guess for the value. So for the initial value, x0, y0, z0, we make it as 0. So for the first iteration, how we need to calculate? In this part, k equals to 0. So k plus 1, which is x0 plus 1 is x1. We need to substitute the value of x0 into the equation. When we substitute the value of x0, y0 and z0 into the equation, we get x for the first iteration equals to negative 0.2, y1 equals to 0.22222, and for z1 we get negative 0.42857. So for Jacobi, when we solve x1, y1 and z1, we need to put all the value from x0, y0 and z0. Same goes for iteration 2 and iteration 3. We need to put all the value from x1, y1 and z1 into the iteration 2. And for iteration 3, we need to put all the value we get from x2, y2 and z2. Same goes to iteration 4 and iteration 5. We need to use all the value from the old value, which is if we do iteration 4 and we need to put the value from iteration 3 and substitute into the equation in iteration 4. So we need to calculate until the value for x, y and z converge. So here is the value for Jacobi hand calculation. Since we just do until the 5th iteration. So we have the value for x, y, and z for iteration 0, iteration 1, iteration 2, iteration 3, iteration 4, and the last iteration 5.
Alright, for the next session, I will explain about how to solve this question using Gauss-Sidel method. First thing first, we need to look at the first equation. Let x be on the left side using separable method, and we will get x equals to negative 1 plus 2y minus 3z over 5. Then we let x be on the k plus 1 term, and y in the k term and z in the k term. For the second equation, we let y be on the left side using separable method, and y will become y equals to 2 plus 3x minus z over 9. And same goes with y. We let y in k plus 1 term, and x, we use the new x, which is the previous x that we explained earlier, and z in the k term. Alright, for the third equation, we let z on the left side using separable method, and z will become 3 minus 2x plus y over negative 7. And we let z on the k plus 1 term, and x and y in the k plus 1 terms too, which is the x and y we got earlier. Now we got all three new equations, x, y, and z in the k plus 1 terms, which is in equation 2 we use the new x, and in equation 3 we use new x and y. So to solve this, first we need to take the initial guess of the volume, which is x0 equal to 0, y0 equal to 0, and z0 equal to 0. So the initial guess, all of x, y, and z is 0. Okay, next we look at the first iteration. We use the x formula that we got earlier, and we substitute the y and z, which is the initial guess is 0. So we will get x1 equals to negative 0.2. For the y equation, we use the x that we got earlier and substitute into the equation, but the z still 0. So we'll get y equals to 0.1566. Lastly, for the z in the iteration 1, we use the x and y we got earlier. So z will become negative 0.5079, and we got the value for the iteration 1, which is x equals to negative 0.2, y equals to 0.1566, and z equals to negative 0.5079. So next, same goes to the second iteration, which is k equals to 1. So for the x2, we substitute y1, which is the y that we got in the first iteration, and same goes to z. We use the z that we got from the first iteration, so we substitute in the x2 equation, and we will get x2 equals to 0.16699. And for the y, we substitute the x that in the iteration 2, but the z1 is from the iteration 1, so we will get y equals to 0.33432. Then lastly, for the z equation, we use the x and y from the second iteration, which is x2 and y2. So z2 will become negative 0.42862, and we got x, y, and z for the second iteration. Alright, for the third iteration, which is k equals to 2, we use x3, which indicates the third iteration for the x. Alright, for the x3, we use y2 and z2, which indicates the y and z we got from second iteration, and we'll get x equals to 0.19090. And y2, we use the s3 and z2, which is x3 we got earlier, and z2 from second iteration, and y3 we will get 0.33348. And for the z, we use x3 and y3, which is we got from earlier, which in the third iteration, and we got z equals to negative 0.4167. For the fourth equation, we use the same concept, which is at x4 we use the y3 and z3 from the earlier iteration, and we got z4 equal to 0.18639. And y4, we use x4 and z3. x4 we use the x we got from iteration 4, and z3 from the third iteration, and we get 0.33121. And for the z, we use x4 and y4 we got earlier, which is z4 equals to negative 0.42263. Alright, for the fifth iteration and the last for hand calculation, we use k equals to 4. Okay, for x5 we use y4 and z4, which is from the fourth iteration, and we got x5 equals to 0.18606. And for y5 we use x5 and z4, which is x5 we got earlier, and z4 is from the fourth iteration, and we got y equals to 0.33120. And lastly, for the z5 we use x5 and y5 from the fifth iteration earlier, and we got z equals to negative 0.42862. Alright, the table shows that this is the hand calculation that we made earlier using Gauss-Sidel method, which is from the iteration 0, which is the initial guess is 0, and into the fifth iteration, which is we got x equals to 0.18606, y equals to 0.33120, and lastly z equals to negative 0.42273.
Assalamualaikum and good day everyone. My name is Muhammad. Next, we will use the formula of the Jacobi method and define it in Mathematica. The formula is d multiplied by x at k plus 1, which is the next iteration, is equal to the negative of L plus U multiplied by x at the current iteration and then at B. Here, D is the diagonal matrix of A, L is the lower triangular matrix of A, and U is the upper triangular matrix of A. Now, we define the diagonal matrix of A. First, we use the diagonal function to take out the diagonal values of matrix A. We call this result D1. Then we use diagonal matrix function on D1 to create a diagonal matrix where the diagonal has values and all the positions are 0. Next, we define the lower triangular matrix. We do this by using the lower triangularized function on A and subtracting the diagonal matrix so that diagonals become 0. Finally, we repeat the same method for the upper triangular. After that, we must define the initial value for our problem. In this case, we use 0, 0, 0 as the starting point because it makes the calculation easier. Now, for the last part, we code the Jacobi formula using a loop. We write the do function for x at n plus 1, which is the next iterations. Inside the loop, we use the linear solve function. First, we put the left hand side, which is the diagonal matrix D2. Then, after the comma, we put the right hand side, which is the negative of L plus U multiplied by x at n plus B. After that, we add the print function so that each iteration result is displayed in matrix form. In this case, we only calculate up to 10 iterations. Once all the code is written, we press Shift Enter on our keyboard and Mathematica will show the results. As we can see, the values at the 10 iterations are approximately 0.18612 for x, 0.33123 for y, and negative 0.42271 for z. We also notice that the answer is slowly converging to the exact solution, especially from iteration 8.
Assalamualaikum and good day. My name is Nur Sarajati binti Azmi. In this video, I will explain step by step on how to implement the Gauss-Sidel method using Wolfram Mathematica. The explanation will follow the coding process from the beginning until the final output, based on the Gauss-Sidel iteration formula, where D is the diagonal matrix of A, L is the strictly lower triangular matrix, U is the strictly upper triangular matrix, and B is the constant vector, while x power of k is the solution at iteration k. To apply this formula, we need to define and compute each component step by step. The first step is we define the coefficient matrix A of the linear system Ax equals to B. Each row of matrix A represents one linear equation and each column represents a variable. This matrix is the main input for the Gauss-Sidel method. Next, we define the constant vector B. This vector contains the values on the right-hand side of the linear system. In this step, we define the initial guess for the solution vector. The Gauss-Sidel method is an iterative method, so it requires a starting value. Here, we choose a 0 vector for simplicity. This command extracts the diagonal elements of matrix A and store them as a vector. diagonal A function, extract the main diagonal element as a flat list, 5, 9 and -7. Now, we convert the diagonal vector into a diagonal matrix D. Diagonal matrix D1 comment creates a new matrix where all elements are 0 except for those in D1 on the main diagonal. This step extracts the strictly lower triangular part of matrix A. Lower triangularized A function returns a matrix with only the elements on and below the diagonal. By subtracting D2, you get the strictly lower part. For upper triangularized A function returns a matrix with only the elements on and above the diagonal. By subtracting D2, you get the strictly upper part. This matrix contains only the element above the diagonal, with 0 elsewhere. The Gauss-Sidel method requires splitting A into A equals to D minus L minus U. Therefore, we multiply both L and U by -1 to match the standard form. Value of X through successive approximation. This loop performs the Gauss-Sidel iterative process. The loop runs from k equals to 1 to k equals to 10. At each iteration, the new solution vector x power of k plus 1 is computed. Linear solve avoids computing the inverse and uses forward substitution. As the iteration number increases, the solution values gradually stabilize, indicating convergence. After several Gauss-Sidel iterations, the solution converges to x equals to 0.1861, y equals to 0.3312, and z equals to -0.42. In this part of the video, I will explain the convergence behavior of the Gauss-Sidel and Jacobi method based on the iteration result obtained earlier. First, let us look at the Gauss-Sidel method. From the output shown, we can observe that from around iteration 7 onwards, the solution value remained almost the same. Next, we consider the Jacobi method. From the Jacobi output, although Jacobi converges more slowly, it will converge to the same solution as Gauss-Sidel. In conclusion, Gauss-Sidel converges faster because it uses updated value immediately. Jacobi converges more slowly because it relies only on previous iteration value.
Now, for comparing the efficiency of Jacobi and Gauss-Sidel method, we test both methods using 100 iterations in Mathematica and measured the time with the absolute timing function. The Jacobi method took about 0.028807 seconds, while the Gauss-Sidel method took about 0.030703 seconds. This showed that for this coding and this problem, Jacobi is more efficient in terms of computation time. Even though Gauss-Sidel often converge faster in theory, each iteration is more expensive. So when the number of iterations is fixed, Jacobi can be faster.
To compare the accuracy between Jacobi and Gauss-Sidel method, both Jacobi and Gauss-Sidel method achieve the same exact solution with 0 error. However, Gauss-Sidel requires fewer iterations. Gauss-Sidel requires 7 iterations to converge, and Jacobi needs 10 iterations to converge. This happens because it updates variables immediately, leading to faster converge than the Jacobi method.
Alright, for the conclusion, we look at 3 main aspects, which is the convergence, efficiency, and accuracy. First, the convergence. The Jacobi method converges at iteration 10, while the Gauss-Sidel converges at iteration 7. So, you can say that Gauss-Sidel converges faster than the Jacobi method. For the efficiency, we can say that a Jacobi is better than Gauss-Sidel because the time consumed to process the data in Mathematica is faster than the Gauss-Sidel. And lastly, for the accuracy, they both achieve exact solution, but Gauss-Sidel is faster, which is the Gauss-Sidel converges only at iteration 7, while the Jacobi converges at iteration 10. So, we can conclude that the Gauss-Sidel method is better than Jacobi method. So, that's all from us. Thank you.